Hello and welcome to this lecture. In this lecture, we are going to start looking at the inner product in R2 and C2, the two-dimensional real vector space and the two-dimensional complex vector space. What is this inner product? How it is used? What kind of problem does it solve? That is what we will see in this lecture. Let us get started. So, before we get started, let us look at the motivation for inner product and such ideas. So here is a problem which is quite common. It occurs in various circumstances. If you're in a lab doing an experiment, you make measurements, you want to plot the data, or this may be data that you got from the internet of various sources and you plotted it and you see this. And you see that this is going to be, this looks more or less like a straight line. But maybe the data that you got was a bit noisy, the measurements you made were not very precise and etc. So it's a little bit off. But still, I really want a straight line here, right? The straight line is sort of visible here, but you can't quite precisely write down the equation for it. So, given these points, how do you fit a straight line to this? So, this is a very interesting question. So, here is one possibility, but how do I know that this is the best one? I could rotate this a little bit, move this a little bit. So, how do I know which is a good one? How do I go with a particular straight line from among all the possibilities that are out there, right? So, for this, we need some notion of distance between points in R2. So, how far are these 2 points? How far are these 2 points, right? So, we need such notions, and we also need some notion of a distance from a point to a line, right? I need to know how far this point is from this line, right? Like that. This seems very close, this seems a little far, this seems a little farther. So, what is that distance notion? So, this notion of distance is needed, and a notion of some sort of angle is also needed. What is the angle of these things? Okay. So, in all these notions, when you have distance, angle and all that, this inner product will play a very crucial role. You will see later on, finally, when we solve this problem at the end of this week's lectures, you will see that the inner product would have played a very huge role. So, this is one of the motivating aspects of this topic. So, let us get into it right away. Okay. So, here is a definition in R2, the real space. The dot product, okay. So what is it? So, before I define it precisely, what is the inner product? Okay. So, inner product is actually a function that maps two vectors to a scalar. Okay. So, function always has an input and an output. What are the inputs of this function? It has two inputs. These are any two vectors in R2. And what is the output? The output is a real number. Okay. So, that is what an inner product is. So, here is notation. If you have two vectors uv in R2, the dot product or the standard inner product is denoted u dot v. Now, notice I am calling this the dot product or the standard inner product. It turns out in theory there can be any number of other inner products defined differently. We will be concerned with what is called the standard inner product or the dot product, and we will denote it u dot v. Okay. So, u dot v is our notation for the dot product. So, here is the definition. Finally, we have the definition here. Let us say u is x1 y1 and v is x2 y2 in the canonical basis. Okay, so in this study, it is very common to just stick to canonical basis. We have seen other types of bases also, but now onwards in the inner product mostly we will be sticking to canonical basis. Okay, so I won't mention this canonical basis too much, but just keep assuming any coordinates they give you is with respect to the canonical basis. So, u is x1 y1, v is x2 y2. U dot v is defined using these coordinates. Okay, notice how these coordinates are used in the definition of the dot product. U dot v is x1 x2 plus y1 y2. Notice the way in which the dot product is being evaluated. The corresponding terms in the two coordinates are multiplied and then you add to get a final number. Okay, so, this is a real number. We can see all of these properties are satisfied. Okay, so, at this point it does not seem like this is any special definition. It seems like some regular definition, but we will see that this definition has a lot of powerful interesting properties and it helps us solve a lot of interesting problems. Okay, so, if you want a picture, x1 y1 is here, x2 y2 is here. These are the two vectors in the coordinate notation. If you do x1 y1 dot x2 y2, you are going to get x1 x2 plus y1 y2. Just rewriting this definition in multiple ways. Okay. So, yeah, so you keep assuming on canonical basis if I do not specify it precisely. Okay, now we go to C2. Okay, now see R2 we could easily visualize. We could see x1 y1 x2 y2. The moment you go to C2 itself, it is difficult to visualize, right? See, C2 is two complex numbers, no? So, C2 is if you say think of a vector in C2, it is u1 u2 u1 is a complex number, u2 is a complex number. So how do you visualize that? You can't, it's already gone to like 4 dimensions, isn't it? Complex itself is 2 dimensions, there are 2 complex numbers, so 4 dimensions, you can't quite visualize it, okay. So you have to rely on the algebra of it and some appeal to what you know before, okay. So but here is the definition: the dot product, standard inner product in C2 is also denoted u dot v. Notice how this dot is the same depending on which space you are in, you have to define it carefully. And here is the definition. Let us say u is u1, u2 and v is v1, v2 in the canonical basis in C2. And notice the difference here. U dot v is u1 v1 bar plus u2 v2 bar. Okay, you remember this bar, right? So this is like the complex conjugate. If you have a complex number z, a plus ib in the complex numbers, its complex conjugate z bar is a minus ib. So notice how in your definition of the dot product between R2 and C2 there is this important difference. The important difference is the second argument, the v argument, the coordinates of v are conjugated before you multiply. Okay, so u1 v1 bar plus u2 v2 bar. Okay, so notice now the order matters, right? U dot v and v dot u will be different complex numbers, clearly, right? They are related but different. We will see what the relationship is soon enough, but the order matters. Keep that in mind. Just don't say u dot v is v dot u, which is true in the real number case, but in the complex number case the order matters, because for the second argument you are taking a conjugate. Okay, so this is the definition. Just to see a few examples: 1 plus I, 1 minus I dot I plus 2, 1 minus 2I. Notice how I am writing the vector notation as just a row vector here. Then 1 plus I, notice how this become 2 minus I. How did this I plus 2 become 2 minus I? It's the conjugate of I plus 2, right? I have conjugate of I plus 2 is minus I plus 2, right? Real part remains the same, imaginary part sign changes, so you get 2 minus I, and then 1 plus I, 1 minus I times 1 plus 2I. These two you multiply, and then you multiply, simplify, add, and you get 6 plus 2I. So you get this complex number. Okay. So notice how the real numbers, real vectors are also present in C2. Now, if you just make u and v as both real, 1, 2, 3, 4, then this reduces to the inner product in R2, right? The conjugate doesn't apply at all, right? If the number itself is real, the conjugate is itself, right? So 3 and 4 remain 3 and 4. So all you have to do is this kind of addition. Okay. So this is how the inner product works. So given two vectors in terms of coordinates and canonical basis, you can define the inner product in this very, very straightforward manner. Okay. I hope this is clear. So this is the definition of the inner product. Okay. So let's quickly see some properties. Here are three defining properties that we will see. First property is conjugate symmetry. I pointed this out already. If you have u, v in C2, then u dot v and v dot u are not the same. Okay. In R2, of course, they are the same, but in C2, they are not the same. The relationship is basically u dot v is the conjugate of v dot u. Okay. So I'm going to maybe prove this very quickly. It's easy to prove. U dot v is this guy, right? V dot u is this other guy, u1 v1 u1 bar plus v2 u2 bar. Okay, if you take conjugate of v dot u, it's the whole conjugate of this guy. Now we know conjugate splits over addition, okay, plus, and then conjugate splits over multiplication also. But u1 conjugate becomes u1 itself, then v1 conjugate plus v2 v2 conjugate, and that is the same as u dot v. So notice how v dot u conjugate is u dot v. Okay, so this is something important to remember. The order of the dot product matters in the complex space, and if you reverse the order, the number becomes conjugated in the dot product. The next very important property is linearity in the first argument. Let's say you have three complex vectors in C2, and a, b are two complex numbers. Then if you do au plus bv dot w, it's the same as a u dot w plus b v dot w. Okay, this is very, very easy, very basic algebra. If you do this, this is the same as au1 plus bv1 times w1 bar plus au2 plus bv2 w2 bar, and then you multiply out, simplify, and then rearrange, right, this first term and the second term here. That gives you au dot w, and then this term and that term here gives you bv dot w. So you can distribute over the first argument. Okay, the first argument is just linear, totally linear. Any linear combination becomes, you do the dot product first and then you do a linear combination later. Okay, so this is just a complex number. Third and very, very interesting property. Okay, this is where you might be wondering why you need the conjugate. Why did we put the conjugate? Okay, the conjugate comes into action here. This is the positive definiteness property of the inner product. If you have a u in C2, a vector u in C2, if you do u dot u, okay, you do a dot product with itself, okay, then it turns out that u dot u is actually a real number. Okay, so previously we saw that if you do u dot v, you will get a complex number. So we do u dot u, then you get a real number, okay. And not only that, you get a real non-negative number. This u dot u is greater than or equal to 0, and when will it be equal to 0? The only way it will be equal to 0 is if u is 0, okay. Okay, so this is if and only if u is 0, clearly u dot u is 0, and if u dot u is 0, then u is also 0. Otherwise, u dot u becomes a positive real number, okay. It cannot be complex. The imaginary part has to be 0. That's very easy to see. U dot u is u1 bar plus u2 bar, right? So, the u itself is conjugated here. Now, u1 bar, you know, is a real number, u2 bar is also a real number. In fact, each of these are basically magnitude square of the u1. Okay, this is u1 magnitude square, this is u2 magnitude square. Clearly, this is greater than or equal to 0, and equality happens only if u1 is 0 and u2 is 0. Okay. So, these three are defining properties. So, it turns out this is how abstractly a inner product is defined. You can start with these properties and show that what I defined as the inner product satisfies these properties. Okay. There are more properties, quite a easy property to see. If you just take an inner product with 0, anything you inner product with 0 is 0. Okay. So, it's but notice how I am doing this abuse of notation. What is abuse of notation? I am using the same 0 to indicate the vector 0 0 here, the vector 0, and the 0 here is a scalar 0. Okay. So, this kind of notation thing is reused. It's no point in writing another 0 here and another 0 here. It's a bit boring. So, you can write, it's clear that when I do 0 dot u, I am thinking of 0 as a vector 0, and then this is a scalar 0. Okay. Okay, so there's also conjugate linearity in the second argument. Okay, so we saw linearity in the first argument. What happens in the second argument? If you do for UVW, AB, W dot AU plus BV, I do a linear combination in the second argument. This is basically A bar, the conjugate of AU dot W plus conjugate of BV dot W. Okay, the proof is left as an exercise. It's very similar to the first argument proof, except that this A and B will now get conjugated. Because of that, this A bar and B bar will come. So, this is called conjugate linearity in the second argument. So now if you have linear combinations of u, u and v, linear combination of w, x, y, etc. If you have to do dot product, you know you can distribute. Whenever you have the second argument being linearly combined, you have to do a complement also. Just watch out for that. As long as you watch out, you'll correctly solve many of these problems. Okay. Okay. Now, we saw that the general definition in C2 was a little bit complicated because of the conjugation, but in R2 many of these things are really simple. In R2 there is symmetry, not just conjugate symmetry, right? For uv in R2, u dot v is v dot u. Both these are equal, there is no conjugate here. That's the first one. Second one is linearity in both the arguments. Okay, so you remember we had conjugate linearity in the second argument in C2. Now, because they are in R2, everything is totally linear. Okay, so you don't need to worry about this conjugate stuff if you are in R2. Okay, finally, positive definite is also there. It's just u dot u, etc. Okay, so in R2 it's a little bit simpler. All these properties are okay. Okay, so that's the end of this short little lecture. So hopefully you saw a quick introduction to inner products. This I'm hoping you're familiar with. It's a very simple evaluation of the inner product. We'll move on to magnitude, distance, etc. in subsequent lectures. Thank you very much.